Please wait 2 minutes. We will start the meeting. उसको नहीं हिलाना, वाईफाई नहीं हिलाना। Okay, good evening to all of. We will discuss fifth assignment. Can you hear me? Please respond. Okay, can you hear me? Okay, thank you. So let's start today meeting. We will discuss here about solar cell, how solar cell is working. So last question is based on diode diode equation. So let's discuss first this. A diode has saturation current 10 to the power 12 ampere and ideality factor n equal to 1. Temperature is given 300 Kelvin room temperature. Find the diode current when the diode forward configuration applied voltage VA or V equal to 0.6. So this is the question and these are the four options. You have to apply exponential upon kT, this expression. Okay, so please solve this equation. Let me wait 1 minute. Here is the equation plus or minus here, sorry. I naught is saturation current or I naught, sometime we called I naught or IS. It's 12 in ampere and is not given. Let me write better. Exponential QVA upon NKT minus 1. N is 1, so we have put N equal to 1 and KT value 26 electron volt. Okay, so put these value and please solve. Are you getting first option or yes or not? Please let me know. Just put E, Q is equal to electronic charge, E and KT. So put the value of KT 0.026 electron volt, E into 0.6 volt. Cancel out, sorry, E is cancel out, V is also cancel out. So 0.6 you have to solve just. Okay, so please solve like that, better way. And approximation, this number is very large, so leave this minus 1 also, so you will get approximation 1.05 10 to the power minus 2 ampere. Okay, so like that question may be asked. So here is the, this is called diode Chokle. Let me exponential VA upon KT minus 1. This is called Sokal-diode equation. Okay, where is I is diode current, IS is reverse saturation current, very small. This is V is applied voltage, VA or V. This is applied voltage like VA. No, we can use in forward, reverse, all direction, not only the reverse. But this IS we can find by the reverse saturation applied by when we diode is made. Q is electronic charge, which is equivalent to E, electronic charge. Boltzmann's constant, absolute temperature, and ideality factor also. N is also is there. N KT. Generally N we can take 1, so I will just write down KT. The equation rise from the minority. Please, this is essential. The equation rise from the minority carrier diffusion across the junction, minority only. When voltage V is applied, barrier height changed by QV and carrier injection changes exponentially, hence current vary exponentially. So nature of this, like in the forward, this is I, applied voltage B here. This section is, this side is forward bias, this, and this side is reverse. Okay, this is microamp, this in reverse, while forward is milliamp. Why microamp and milliamp? Can anyone have any idea about this? In reverse, only microampere current will flow across the junction, while in forward configuration, milliampere current will flow as a huge order. Why this? You know, barrier height, when we discuss reverse and forward, barrier height in the reverse condition is huge. So minority number of charge carrier, which is minority, is cross the junction very less. In the forward condition, barrier height is small as compared to reverse. So minority charge carrier get transfer from one side to another side is huge as compared to reverse. So here is the applied condition. Barrier height will get less or get high. In reverse condition, barrier height will rise, while in forward barrier height will lower. Forward, let me recall you. reverse, while in forward. So this side, this is too high as compared to this. Okay, so electron easily gets out from air to air while need that much energy. This EV, applied voltage, air is very less. That's why air is milliamp order current, air is microampere. Okay, let's move. This is your next question. In a PN junction diode under illumination at a short circuit current condition, okay, which option will correct according to you? Yes, please. PN junction diode under illumination, a short circuit current condition. Let's say solar cell, or the photocurrent flow from P side to N side of the diode. P side to N. Minority carrier move across the depletion region due to drift. Quasi-Fermi levels are aligned across the diode. Recombination and generation current are balanced. So option B is correct. Minority carriers move across the depletion region due to drift. Let me explain more. This is P and N, and on elimination, let's say H nu, which is higher than the band gap of this PN diode. Okay, when electron and hole pair are formed here in the depletion region, here is a applied electric field, built-in electric field, which is electron is force. So these electron and holes pair due to this electric field, they are drift. Okay, why? Only drift is happen due to the electric field is responsible for drift current. Okay, so hole and electron will get drift. What will be the direction of hole and electron here? hole diffuse this side, electron, sorry, drift. Am I right? Hole flow, electron flow opposite to the electric field always. Please remember. Also this side is plus plus plus, this side is negative negative, so negative repel, and electron and positive charge will attract each other via electric Coulombic attraction. So minority carrier move across the depletion region due to drift. Sir is also explaining the lecture. Next question. One minute. Which of the following are correct for direct band gap material in the dark condition? Space charge region dominate the total dark current. Drift current dominated to the total current. Diffusion current dominated to the total current. Total dark current. Dark current is negligible. Radiative recombination current can be significant. Direct band gap material in dark condition. Dark means no exposure of light on p-n junction. Okay, so these are the option. Correct option. Space charge region dominated the total dark current and radiative recombinant current can be significant. Please see in from the lecture. p-n junction in dark. No generation of the carrier. If no light, no generation. Valid depletion approximation. No generation recombination in the depletion region. Low level injection. Electric field is inside bulk. In the bulk also the concentration gradient is 0. Diffusion current dominate the total dark current. Initially diffusion will happen, but after that when the equilibrium is achieved, so this is question about after that the equilibrium. p-n junction is totally formed, and what is next? Drift and diffusion will balance. So direct material gap now put in the dark condition. Now think up from here. Diffusion current dominate the total dark current. No, drift and diffusion only significant when the initially before the equilibrium. Okay, so equilibrium already is there. Dominated the total dark current. and additive recombination current can be significant. In direct band to band transition, additive, which is known as additive band to band transition, valence band to conduction band. Non-radiative, which is due to the impurity or subphonon, or and so which is in indirect or impurity material. But radiative recombination is significant in direct band gap. So question is about direct band gap. So this is why this, and space charge region dominated the total dark current. Total dark current only on due to the space charge in the depletion region, or leakage current, or say in other word, leakage current will flow from only the space charge limited current or in the depletion region. Okay, let's move. This is also, let me show you, wait. Please see also depletion approximation. No pre-charge carrier in the depletion region. In the region away from the junction, depletion region, minority carrier determine the current. Only minority carrier move by the diffusion in the region away from the depletion region, in the bulk region only. And leakage current will flow from only the space charge or junction. Minority, 1 minute. In the region away from the junction, or depletion region, minority carrier determine the current. Okay, let's see the next question. Which of the following statement are correct for an unbiased PN junction diode? There is no generation or recombination in the space charge region. Hole move from N region to P region, while electron move from P region to N region, and the carrier concentration is much above the equilibrium concentration in both P and N region. This is not in the dark condition. This is eliminated. So the quasi-Fermi levels of the electron and hole are equal. Hole move from P region to N region, while electron move from N region to P region. Okay, B and C. So you are correct, B and C. Hole move from N region to P region, while electron move P region to N region. So see, this is in non-equilibrium condition when we eliminated, and short circuit condition, which is V equal to 0, no net recombination SLC in. So here is the concentration. You can see this is move up, also the move up, because number of charge carriers are increased due to the elimination. Okay, so holes move N region to P region, and electron move from P region to N region. Carrier concentration is much above the equilibrium concentration in both. Okay. Which of the following is correct statement for the elimination PN junction diode? So recombination current in the diode balance the photocurrent at open circuit voltage. How? Recombination current in the diode balance photocurrent. You know two type current are there. One is diode current, other is and second is illumination. They are in opposite in nature. One direction this, other direction this. They are opposite in direction, so these current will balance. Or recombination current, which is known this referring to the recombination current, or illumination recombination means. Current in the diode balance the photocurrent at the open circuit voltage. Wait 1 minute. Okay, here also the same. Let's see which of the following strategy to use improve the quantum efficiency of solar cell. Yes, please. Quantum efficiency. What is this meaning? Quantum efficiency. Let me give to you. We have a one, let's say, device or solar cell. I put 100 photons h nu, which is greater than the band gap energy, and material generate electron holes pair, okay, which we will collect by the external circuit from the load or somewhere here. So these number of electron, how many number of electron and hole with respect to the 100 photons, let's say we will get 40 or 80. So this is 80%, let's say, quantum efficiency. Okay, two type of quantum efficiency, internal or external, is further classification. Internal means, let's say, without internal, one is external. External means, let's say, any reflection losses, so only we will reflection, transmission, absorption will happen here. So let's say we have initially 100 photons, so we will take these as a reference from the without loss, with loss. So whatever we get electron hole pair, we will take only the initial photons which will be put on the solar cell. But in an internal case, let's say we have 100 initially, let's say 20 is reflected, so inside only let's say we have 80. So these 80 is take the reference with respect to, let's say we have get same like that 80 here, like that 70. So 80 by 100, this is this is, so reference is in the internal. We will take care about the reflection losses and all these, then remove minus these, and only count only these photon which is inside the material, which is cause the electron hole pair, generate the electron hole pairs. Why external, just we don't know what is the number of reflection, just take the initial point and check the number of electron hole pairs which is measured by the current. Okay, got it? Clear this point, internal and external? So this is the quantum efficiency which is measured by the current. Generally put the light which is fixed wavelength, monochromatic light, different color of light, red, blue, violet, and check the current generally. So for quantum efficiency we will improve. We don't want to the losses, so surface specification we will do surface specification, so reflection losses will get lower, and anti-reflection coating we will also apply on the surface, and texturing on the surface. So these are reduce the losses from the front, reflection losses generally. Okay, true is just we put the light initially, whatever we will give the power with respect to this, what number of electron hole pair will, what is the number of electron hole pair or current. So we should take the from the initial, from the top of the any material, and so we will apply these strategy: texturing, surface specification, anti-reflection coating will reduce the reflection losses. So number of photon will get inside more. If number of photon inside is more, number of electron hole pair generate more, will improve the current. Here also effect of the material quality, other factor also. So what is the quality of the material? Okay, let's next question. Recombination in the bottom layer of the top illuminated solar cell can be manifested by, so option is also, answer is also, but why? Let's see. Drop in quantum efficiency at log wavelength. You can see in the picture recombination in the bottom layer. You have top, let's say photon of lights, this is top, this is bottom. Drop in the quantum efficiency at long wavelength. Initially, short wavelength is absorbed by the top layer from the top side, and longer wavelength will get inside. So longest wavelength is come at to the bottom, long lambda at the bottom side. If recombination is at the bottom layer, will happen if the losses is there or recombination at the bottom layer, so quantum efficiency drop along with the longer wavelength side. Let's say quantum efficiency curve will like that. Okay, this is wavelength or lambda, let's say 200 or 300, 250 move. So what is the question? Recombination, let's say bottom, so efficiency will drop like that, quantum efficiency. This is without bottom layer recombination. This is with. Okay, so curve should be for ideal like rectangle. This is 1 across 1 or 100%. We will multiply by 100, in percentage will get 100%. Quantum efficiency at the band gap will drop 0. Okay, but not ideally. So due to the losses, this is front side, this is bulk, and this is back side. Back, front, bulk. Okay, so drop in quantum efficiency, question will can ask by the graph also. Let's say, let me give to you two curve. Let's say one is like this and other is this is more square like that. So drop in the like that. So this is bottom side losses as compared to this. Okay, see the next question. Following parameter doesn't affect the quantum efficiency of photovoltaic device. Absorption coefficient, thickness of the device, applied electric bias, surface quality. As we can see, surface quality is affect, and absorption, if the number of photon absorption is high, means number of electron hole pair will be high, so this will be affect. Thickness, if you take too much thicker, let's say all light will get trapped by this material. If you take less, let's say, so this is I by I naught to the power minus u, absorption coefficient and thickness, so drop by exponentially, which is, and so thickness is also matter here, so this is also affect. But applied electric bias will not affect the quantum efficiency. This is related to the material, and quantum efficiency only give the characterization of the material, only affect by the material quality or material surface, front, back, and inside defects, not by the applied bias and electric field. So clear to you? Applied electric bias, or you can see surface reduce reflection losses, also increase the cell thickness, light trapping. All these will affect the quantum efficiency, but not. So let's solve this question. A solar cell is illuminated with the monochromatic light with wavelength is 600 nanometer. Incident power 5 milliwatt. Photocurrent is 1.5 milliamp. Find the quantum efficiency. Quantum efficiency incident power with respect to output. You have incident power, wavelength of photon, and output is current. So you have to find the quantum efficiency. So apply please this. Quantum efficiency here is incident photon IPH, photocurrent means output. This is milliamp you have, and H is Planck constant, C is also constant, light speed. And Q is electronic charge 1.6 10 to the power minus 19 coulomb. Py is incident power. Incident power 5 milliwatt and lambda. So please put this value in this equation. Can you try? Please try. Yes, please. Let me show you the solution. Please see the solution. Quantum efficiency 1.5, current is given, so let's put in the ampere, and Planck constant 6.6 into 10 to the power minus 34, and speed of light 3 into 10 to the power 8, divided by electronic charge and incident power and wavelength of the light. So you will get around 41%. Clear? Okay, let's move for next question. Following is are correct for the design and operation of the efficient photovoltaic device. Band gap is band gap of the semiconductor. We want to efficient solar cell. So what are the parameters should be carefully checked to get higher efficiency? Yes, please. So option R is given here, low movability of the charge carrier, and is R correct? Okay. Minimization of the recombination rate throughout the device, high surface reflection from the cell surface, maximize the absorption of the photon with E is greater than the EZ, and low surface reflection from the cell surface. As you know, let's say you have energy of incident and material has band gap EZ. So first is EZ greater than should be only will absorb the material incident photon. So solar cell only will work give you more current and more output if absorption will high absorption. Okay, and losses, reflection losses from the surface, losses should be minimum because these are loss from the surface, not generate the current, will not generate the current, and defect also less inside the material. So now please give me the your answer. Movability means, okay, minimization of the recombination rate through the device. Low movability means electron or electron hole pair move very low. So movability of charge carrier should be high, long, and carrier lifetime should be high, and so B, D and E are the correct option here. Low surface reflection from the cell as I discussed, and D, maximize the absorption only will generate high output. High reflections should not be this. Reflection losses from the cell surface should be minimum, not high. And what is this? Minimization of recombination rate through the device means we will control the losses inside the recombination of charge carrier is very low, should be very low, otherwise electron and hole pair generate and recombine again inside the material before the coming to the outside. So we want to this electron flow from the circuit before the recombination. and this should be high, not low. Okay, yes, related to the moment of the how fast is moving. Other factor also include in this, but indirectly or directly related to the movement of the charge carrier. Clear? Let's move for next question then. Which of the following device characteristics are determined with JV curve of illumination, PN junction, solar photovoltaic? Okay, let me. Diode has like that. This is dark, only PN junction. When we put the light of PN junction, this curve is shifted. This is solar cell output. J total equal to J dark minus J photocurrent. This is J total current on the, and this is applied voltage. And these are in opposite in J dark, or let's say this is J diode current minus J photocurrent. So which of the following device characteristics are determined with the JV curve? Maximum power point. So you have to find out. Let me. This is VOC, open circuit voltage. This point is JSC, short circuit current. And you have to find the maximum point where is multiply of J and V is maximum. Let's say this is J amp, maximum current, maximum voltage, VMP. This is P max point, maximum power point. So maximum power point is not the product of the VOC and JSC. This is not correct. One minute. Maximum extracted power is VMP, IMP, or J can you simply I. Both are similar. This is as area divided by area. Current divided by area is known as density, current density J. So both are similar. Maximum extracted power is Vm multiplied by Im, with Vm is less than or equal to VOC and Im is less than or equal to ISC. This is, you can see from the curve, this will be get up to VOC but not beyond this, or always will less. At maximum power point factoring the curve tangent will give you 0 or not. So this is the characteristics at maximum power point. Tangent partial derivative of voltage will give you 0, and B maximum power also this. Clear? Okay, so let's see the next question. Then let's say calculate one question. Calculate this. A solar cell deliver P maximum power 18 millivolt. I maximum current is 30 milliamp. Find the V max. You know power is equal to I into V. So you have to find V max. Please apply this formula and find out the answer. You can take 2 minutes for this, but solve this numerical question. Others, please try to solve. You have to just 18 milliwatt equal to I max. You have 13 milliamp, and you have to V max. Milli cancel out. 18 by 30. Okay, will give you 0.6. Yes, very good. So please see the solution. This type question may be asked. Simple, but solve this type of question will help in exam. The open circuit condition in a PN junction photovoltaic device is correctly represented as. Okay, let's say you have this is characteristics IV, I and V. This point is known as ISC, short circuit current, open circuit voltage, and one point is maximum on, let's say maximum power point here. This VM V max, here is I max. So here is a applied voltage, here is a V0, V equal to 0 here. So this point is V equal to 0, I equal to ISC, and this point is voltage equal to VOC and current equal to 0. So V not equal to 0, we talk about this point, but current is 0 है. And I have already told you short circuit current and all these things. Okay, no. So this is open circuit condition. Open circuit means no flow of current, means infinite resistance, you can say in other word, or no external path, no current, photo generated current is accumulated, Cauchy Fermi levels are split, and voltage build up across the junction. So current is 0, but voltage is open circuit voltage. This is condition of for open circuit device. Clear? Okay, thank you for your response. See the next question. The photocurrent in a PN junction diode depends on photocurrent. Let's say you have device, and let's say, let me put the sunlight H nu, which is energy, is greater than the band gap, and you have device, and you have to collect, let's say collect power from air, means you have to collect the number of electrons or current. This curve is like that, B and I. So photocurrent in a PN junction diode depends on applied electric bias, intensity of the illumination, quantum efficiency, and diffusion of the majority charge carrier. Yes, please. So let's I put 50 number of photons. Current will be less. If we put 100, current will high. So this is intensity dependent. Intensity of the illumination. This is related to this. And applied electric bias means you have to forward and reverse bias. If you applied high, barrier will lower and up according to the applied bias. Quantum efficiency, this is material quality dependent. What is the quality of the material? So photocurrent, you have to focus on the photocurrent. Diffusion of the majority charge carrier. So how we will improve the photocurrent of the device? So as I discuss, intensity is, if the number of photons is high, current will be high, and also the material quality, which is determined by the quantum efficiency. If the material is defective, current will be less because charge carrier recombine inside the material. Applied bias is not the material quality or not the, this is only related to the barrier height, not the generation of the charge carrier. Diffusion majority charge carrier, only minority charge carrier will take in the current, no? So this is not also. Okay, 1 minute, let me show you other things. This is, we will discuss this in the fill factor. So this is the question. Okay, the improvement in the fill factor of the particular solar cell device would necessarily lead to fill factor. What is fill factor, do you know? Let's say you have a stat line, this is ISC, this is VOC, this is ideal and area of this, and I have other, let's say this is the curve for other solar cells. So this is area. So area of the ideal solar cell with respect to the real cell is known as fill factor. So this is related to the total power output from the device. So this is give about the quality of the solar cell, tells you what is the quality, what is, how much your device is good. Fill factor, ideal solar cell, real solar cell, area under the curve of JV curve of the ideal solar cell of the real cell with respect to the ideal, which is known as fill factor. So this is shunt should be, this is give the idea about the shunt resistance. This side is series resistance. Okay, so series shunt resistance should be infinite, series resistance should be 0 ideally. So this is also about tell you fill factor about the series and shunt. What is the, how much series resistance inside the your in material, all these. So increase in the open circuit voltage, the improvement in the fill factor means increase in the open circuit voltage, decrease in the bias dependent current, increase in the short circuit current, increase in the maximum power extracted. Yes, please. Let you have ideally this is, but let me take one solar cell which is curved like that, which is at the same point, but this area is different from the one And let me take another one which is curve like that. Red one, this is first, second, third, and so on and so forth. Fourth. So curve 4 has less area inside the IV axis, 3 is more, 2 is furthermore, 1 is highest. So 1 has higher fill factor, highest fill factor, then second, then third, then fourth. So JSC is same, or IESC source circuit is same, VOC is same. Only the series and shunt resistance will affect this curve nature. So improvement in the fill factor means extracted power will also increase. Am I right? And other option will also maybe right. Please check. Increase in the short circuit current, not. Short circuit current will not affect because this is related to the incident power and material quality, which is same. Material is same, only the fill factor, let's say, improve. How? Increase in the open circuit voltage, let's say same. This is also not correct. Decrease in the bias dependent current. What is this? J total is J bias or J junction and J photocurrent. If this is get and this is J bias is initially and minus due to, if this is less, this current, total current will be is get high. So this is also related to the improvement of the fill factor. And explanation only here, sorry, this is question 13 explanation, this and this. Fill factor is defined as VMP, JMP or IMP, you can say in other word, divided by VOC and JSC. Okay. VOC, JSC, J max or I max, you can say. I, let's say, reside, then let's say assign I, V max. So output from this solar cell, highest output from the solar cell divided by VOC JSC, which is known as fill factor. So P max you can also calculate. P max also fill factor, VOC and JSC. Fill factor increases means P max also increases. So D option is correct. And illuminated current also is JSC, J minus J dark. If J dark is less, is get closer to 0, means total current is improved. So curve become more square. Okay. And physical improvement, why this is fill factor? Recombination decreases, dark current decreases, series resistance decreases, and shunt resistance also may be increases. Shunt should be infinite. Reducing the bias dependent dark current also. Clear? Okay, thank you. Next question, the expression for the current density J net in an eliminated PN diode is J net equal to JSC minus J dark. Which of the following is correct between V equal to 0 and V equal to VOC? Here JSC the short circuit current density at 0 bias, J dark is bias dependent dark current, and J net is total current. VOC is open circuit voltage. Okay. So here is V equal to 0 and here is equal to V equal to VOC. So you have to discuss, you have to take this region, let's say. Okay. Question about this region. And J net also JSC minus J dark you have given. So which option will be correct according to you? A, B, C and D. This is negative axis, fourth quadrant. B. Answer will be D. This is negative current. Total J net is less because this is negative axis in the fourth quadrant. Total current is negative. You can see the curve is on the negative axis. Current will only, total current will always is negative. So J dark according to this equation will be greater than 0, let's say is positive, and JSC short circuit current, which is assigned by the photocurrent, related to the photocurrent, which is negative. Okay, opposite in direction, but J dark and J short circuit current, which is related to the photocurrent. So this is if negative, then only the J net total is negative, and this is positive but not greater than the JSC is greater than in mode. Amplitude of JSC is very high as compared to J dark. If JSC is negative, then J net is total negative. And curve, from the curve you can see the total current is on the fourth quadrant, means total current is negative. Wait 1 minute. At short circuit condition, applied voltage is 0, means dark current is 0, only the J net is only JSC. At open circuit voltage means J net is totally zero, both dark equal to J saturation. Between this 0 to JSC vary. J dark is greater than 0 but less than JSC, and total current is less than 0. Next question, for a PN junction photovoltaic device, as temperature increases, then mainly VOC decrease, increase, or both? VOC and JSC both increase or decrease? Okay, so mainly VOC decrease because PN junction photovoltaic device temperature increase because of VOC open circuit voltage is decreases. Next question. Okay, this is the current density for PN junction under elimination is given by J equal to JSC minus J naught multiply factor exponential QV M cavity. M is ideality factor at open circuit condition. These are the options. You have JSC minus J naught exponential QV divided by MKT minus 1. So at open circuit condition, you know open circuit, this is V equal to VOC and I equal to 0. So total current is 0. Please put the J equal to 0 and solve. J is equal to, let's say, J naught exponential term also. So D is also correct, and A you will VOC, V equal to put VOC in this equation and solve. Let me solve for you. JSC divided by J naught exponential QOC on MKT. Take log both side. Log this is cancel out, and this is Q. So you have to log plus this one is also get away, and MKT divided by Q. This is VOC. Clear? Please check now. M, let's say put 1 for ideal factor expression. You can put M equal to 1 for silicon or other. Generally we will put, if M is not given, let's say put M equal to 1. Clear? At open circuit voltage, Okay, thank you. So now calculate this question, this mathematical. 1 minute. Okay, this is the question. A solar cell has JSC equal to 35 milliamp per centimeter square, J naught 2 into 10 to the power minus 12 m per centimeter, m equal to 1, T equal to 300 Kelvin. Find VOC when the cell is at open circuit condition. You have to apply this formula at open circuit. Please find the answer. You can take 2 minutes for this question. For numerical question, please give me the answer. Okay, please take 2 minutes. हाँ सर, हाँ सर बोलो. हाँ अभी करता हूँ 10 मिनट में. Yes, please answer. Answer B. And did you get answer B? VOC equal to KT by Q ln, you have to put JC by J naught plus 1. KT by Q, let's say KT 2.26 electron volt, and Q is E is cancel out, So V is 0.026 volt. Ln JSC is 35 milliamp and J naught is 2 into 10 to the power 12. This is minus 3 in ampere plus 1. Please solve this. This is very less number and this is very less. Let me check with calculator. Okay, then this minus 12, this is get upside. 35 divided by 2, 17, 9. Okay. Okay, approximate you will get. Okay, thank you. Then your answer is approximate. Here approximation may be applied because this 1 minute 10 to the power. Multiply by 0.026. Okay, you will get this is 0.63 volt, which is approximate near is P. Okay, you are correct. See the next question. Consider a P plus N silicon diode with acceptor and donor ion concentration is given respectively. The whole diffusion coefficient in the N side is 10 to the power 10 centimeter square per second. Tau is also given you 10 to the power minus 7 second. Active area is 2 10 to the power minus 4 centimeter square. The reverse saturation current in diode will be. Okay, so see, this is the reverse saturation current equation. I naught equal to Q area of the device, diffusion coefficient, P number of holes carrier and diffusion coefficient of holes. So you have to calculate P of N, P side number of holes in N side. Okay, and Ni square divided by this is in divide Pn into Nd. Here we apply. Here we will get Pn 10 to the power 4 and diffusion length diffusion coefficient into tau. From here you will get 10 to the power minus 3 centimeter. Now you have whole number. Now electronic charge, area is of device, and this is diffusion coefficient, and 10 to the power minus 3 diffusion length. All number we have put 10 and we have diffusion coefficient 10. Put all these number, you will get 3.2 into 10 to the power minus 15 ampere. So this is the equation, but we have applied 1, 2 and 3 equations here to solve this equation. Okay, this is next question. A PN junction solar cell has VOC and JSC respectively. A second also you have cell same area and VOC GSC are different. Assuming both are ideal diode equation, they are values VOC and JSC when they cell are connected in parallel. You have to connect in parallel. Let's say let me collect here power output. So in a parallel VOC will you have to calculate VOC is same will be because V output is same across the both. Current will be add up J1 plus J second. So you have to apply this concept. Answer will be C, but how? Let's see. This is, we know the diode equation, or we can put in other word, other style like that. J naught we will calculate like that, divide by this. So from first J naught from one cell, second cell also we have calculated. Now the cell in parallel, so voltage across the both are will be same, I have discussed like that, and current will be add up. So 20 and 16 is given to you, so will be 36 milliamp. And at open, now let's say this is the point. At open circuit condition, both current will be add and voltage will be the same. Open circuit means VOC. So this equation current, I have put VOC, both VOC same for first and second, and VOC from here you can convert into the VOC equation. Wait, what happened to this? Okay, so this is the final expression, but this is concept. You have to apply this concept. Okay, after put the JSC1 and JSC2, 20 and 16, J01 and J02 we have already calculated. You will get 0.52. Okay. This is next question. Consider a PN junction diode of area 2 centimeter square under illumination 100 watt per meter centimeter milliwatt per centimeter square, given short circuit condition density 25 milliamp per centimeter square and open circuit voltage 1 volt, generate maximum power 45 milliwatt. Fill factor, you have to calculate fill factor. So what is the formula for fill factor? I am maximum V max upon I or J, you can put whatever you give J, then you have to put J in the both, upon VOC into JSC. Or in other word, other formula is also this P max, this is related to the P max. This is P max, nothing else. So you have to maximum P max 45, VOC is given to you 1 volt, generate, and now we have to put IA, VOC and ISC. ISC divided by A equal to JSC. So you have to multiply by area into JSC. So area is given to you 2. So 2 into current, and maximum you have already 45. You will get the answer 90%. Okay. So this is your last question. Please see. Consider a PN diode of area 1 cm square, illumination 1000, 100 watt meter percentage, 100 milliwatt per centimeter square, short circuit current density 24, VOC 2 volt, maximum power 40 milliwatt, power conversion efficiency. We have to calculate the efficiency of the device. So it has VOC JSC fill factor divided by, or you can write P output upon input, incident power, or P input. So you have P input, this is P input 100 milliwatt per centimeter square. You have to calculate P output. How you calculate? You know fill factor. From there you can also calculate. So output related to VM, Vmax, Imax. So this is fill factor. You can correlate it with Vmax, Imax upon VOC into JSC. So multiply VOC, JSC and fill factor, you will get P output. So this is P output, nothing less. So here P max you have 40 VOC JSC, fill factor is 83. Let's say put fill factor and VOC JSC. You will get the efficiency 39.98. Okay. Okay, so this is your last question. Thank you. We have discussed 20 question, numerical and all R types. Okay, so let's meet again, if you don't have any doubts, on next Monday with 6th assignment. Thanks to all of you. Okay, let me close the session.